In this video, we are going to see a full digital design example. We are going to design the circuit proposed in example 1, and we are going to obtain an optimum circuit in 2 levels of combinational logic, which means we are going to do it by using a normalized form, sum of product or product of sums. At the example 1 in the unit, we already made the formal description of the circuit based on the problem we had to solve. So we need to implement a logic function. We have assigned inputs and output signals. And this is the truth table of the function we have to do. So basically, in our alarm system, it means that when the alarm is connected, which is when A is equal to 1, the alarm will be activated in any case if I detect presence or if the door has been opened. And when the alarm is not activated, this part of the table here, the alarm will only ring when the door is open and presence is detected, meaning that you probably left the door open, so you want to be signaled. So once we have the truth table, we need to find the minimal expressions as a sum of product or product of sum, because the problem says an optimum two-level combinational circuit, we have to find the most simple expression. So we have to try both with sum of products and products of sums. So we will start by drawing a Carnot map, 3 variables Carnot map. And just copy the information to the map. This is A, B, C, 0, 0, 0, 1, 1, 1, 0, oh, 0 and 1. So my table is this one, 0, 0, 0, 1, 0, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay. So to minimize that, we start finding my prime implicants. It's very easy in this case. This will be a prime implicant. This will be another prime implicant. This would be another prime implicant. Using the ones, the mean terms. Okay. So we have an expression for my function that is f is equal to AB plus this term could be BC plus, and this term could be AC. Okay, so this is a sum of products with 3 terms, and every term has 2 literals, and we have no complements here. Okay, now we'll do the same with the product of sum. So I will try to copy this just to make it a bit faster. Great. Okay. I will remove the marks from here. Great. And now we will go and find the solution using the product of sums. Okay, so we start with the max terms. The function is very much the same than before. So this and this is an implicant with no adjacent implicant. So this is a prime implicant here. We have another prime implicant here, and we have another prime implicant here. So the expression could be, this one is A plus B. This one, this implicant will be B is 0, C is 0, so it will be B plus C. And this other implicant, A is 0, C is 0, so it will be A plus C. So with in an expression like this, the circuit we can derive from here directly will be a circuit where we use a first level of AND gates to make the products and a second level of an OR gate to do the sum. So from here we will obtain a circuit that is called an AND OR implementation. Okay, first do the product, then do the OR. From here we can do it with a circuit that where we calculate the sum terms with OR gates, followed by a NAND gate to do the product, to do the AND operation of everything. So it will give us a two levels circuit in a OR AND structure. Okay, so sum of products translate into AND OR, and product of sums translate into OR AND. What's best, to do it like this or to do it like this? So we want the most simple implementation because we want to save gates, we want to save resources. So we have to evaluate what's the cost of doing this or doing this. The cost can be evaluated in different ways. And the first thing we have to think about is that we need to make complements or not. Because if I have to complement the variables, it means that additionally to the AND and OR gates, we will need to use inverters. It's not a problem in this case because we don't need to complement any variable. Okay, so we don't have the inverters. And now to evaluate the cost, we will normally count the number of terms, because if I have more terms, I need more gates. But we also have to count the number of literals. It means the number of literals in each term. Because if I have more literals, my gates will have more inputs. More inputs mean more transistors needed to build the gate. So basically, the cost can be evaluated in different ways. What we can do is that we can define a cost function or cost method where we have already defined that, where we count the number of terms together with the number of literals and together with the number of complements. So we assign the same cost to the terms and to the literals and to the complements. Okay, it's not that bad because in modern technology we mostly use complementary MOS technology, and basically in that technology every input of a gate needs two transistors. Okay, so an inverter has one input and needs two transistors. An AND gate will need two transistors per input that it has. Okay, and also the output gate, which is this number, we will add the terms, all the terms, will need an input for each term we include in our expression. So it means two transistors per term we have in my expression. So more or less we use the same real resources in a real circuit, for the terms and for the literals and for the inverters. So this gives us a very simple way to evaluate the cost. So in this case, I will say that the cost could be the number of terms. We have 1, 2, 3 terms, plus the total number of literals in all the terms, which is 1, 2, 3, 4, 5, 6, and plus the number of inverters. Okay, that is 0 in this case. Now here the cost would be, it's easy to see it's going to be the same because we have three terms, three sum terms. We have 6 literals in total, 0 inverters. So it's cost is 9, the cost here is 9 as well. Okay, because we have the same cost, we can use either this expression or this expression to build my circuit. So we will draw the circuit in any case. Okay, so from here we just, to do the AND operation, we will use an AND gate. To do this other term, we will need another AND gate. To do the other, another AND gate, and we finally will use an OR gate to sum everything. Okay, so my circuit could be something like this. The drawing's not very good, but so this could be term A, B. Here we'll make B and C, and finally here we'll make A and C. Okay, it's important to draw the circuit that is clear what is connected. So this gate will make the first product AB, this is the second BC, this is the third AC, so this OR will add all these terms and will give the function f. Okay, in a very, very similar way, we can use this expression. So in this case, the first level is made out of OR gates that will do the sums, A or B. Next one could be B or C. Last one will be A or C, and all these can be done. We don't actually need, in this problem, we don't need to draw both circuits, because we have seen that they have the same cost, so we can just use one of those. Okay, we select the one with the lower cost or one of them, but just to have an idea. Okay, another point about that we have told about the cost is that another detail will be, if we use 4 gates here, we use 4 gates here, we use 3 AND gates here, 1 OR gate here. Here we use 3 OR gates and 1 AND gate. If we go to the details of the technology, it's not necessarily true that AND gates have the same cost than OR gates. Okay, so still we may use one circuit or another depending on more technology details, but if we don't have those details, general evaluation of the cost as we have done here is enough. Okay, so that's it. Thank you.